The last two topics, that is model predictive control and linear quadratic regulator, they are all based on linear models, right? Linear means simple plan, simple control systems, okay? But if you look at actual controls, like what you see over here, right, there's a cart, and on top of that, there's a pole, right? Um, Sometimes we call it inverted pendulum, right? Pendulum is like this, and this is inverted, right? So that's why it becomes a control problem, right? You need to push the cart back and forth or left or right and balance the pole vertically, right? And in the same time, you want to move the cart to a desired position. So there are two controls. One is to stabilize the pendulum, right? And then move the cart to a desired position. So it's an advanced control system, right? But if you simplify uh, uh, the state of motion, right? If you want to see 360-degree whole position, it's really non-linear. But if you look at it as a vertical, very close to vertical, maybe plus or minus 10, 15 degrees, right? Then you can reduce the linearity, non-linearity rather, and make a linear model and design linear quadratic regulator or model predictor, whatever it is, all linear controllers, and stabilize the plant. Okay. But if it moves more than that, some 30, 40 degrees, sometimes going like downwards, of course, your linear quadratic regulators, your linear controllers are helpless, cannot stabilize the plant. So in that case, you really need some sort of nonlinear controls. Okay, so this is the first time we are going to look at how we can design and build a nonlinear controller. Okay, so that is the topic today. Um, there are several nonlinear controllers, but today we are going to look at feedback linearization, right? So that is a nonlinear controller. Okay, so let's get going. This is a methodical treatment today. I'm not going to straight away jump into nonlinear controls, but I'm going to walk you through the entire process, starting from simple controllers and eventually end up with the nonlinear control. Okay, right. The first thing is to model the plant, right? So uh, over here you can see the cart and the pole, right? And the coordinates. For example, the pole angle is theta over here, right? And position of the cart is measured rightward, x and x dot, position and velocity. And if you look at the pole over here, right, there's some tension in the pole, some tension in the pole. This tension is a force actually, pulling the disc over here, right, downward, right? Let's call this a pendulum. It pulls the pendulum down on this end, but on the other side of the pole, it pulls the cart upwards. So you can see the two arrows. This is how this force is acting on one hand on the pendulum, on the other hand on the cart. Okay. Now, what we do next is we take the cart without the pendulum and draw all of the forces acting on it. And you can see the mass of the cart is capital M over here, and we are pushing it using a force that is U over here, pushing it rightward. Sometimes you can take it, pull it backward. Then it is a negative force, negative U. Okay, whatever it is. Then you have this Bx dot, which is the drag or friction. As you move forward, there's a friction, right? The friction is proportional to the speed. So therefore, let us call it B times x dot. So this is opposing uh, force. All right. So look at the direction, it's coming this way. So if x dot is positive, that is positive velocity, this is against. And if the cart moves leftward, the other side, then you know x dot is negative, right? Then this force would be from left to right, the opposite direction. So the sign of x dot will take care of this friction. It's always against the motion, right? Positive or negative. And on top of the cart, you can see two forces. That is the pole tension is F based on the angle theta, right? You have F cos theta upward force and F sine theta horizontal force to the left. So these are the forces acting on the cart, right? So you can easily write down this first equation over here, right? For the motion of the cart horizontally, rightward from left to right, okay? So the force is U, uh, and then you have F sine theta is a negative force, so minus F sine theta. And also there's another force Bx dot, also negative, right? These are the three forces acting on the mass. There are no other force, right? And this resultant force causes the mass to accelerate. Therefore, this is equal to mass times x double. So that is the first equation. There's no motion upwards for the cart, so therefore that's the only equation for the cart. Then if you look at the pendulum, this is the pendulum, okay? It has its own weight downward, that is mg. It's not written here actually. And also you can see the tension of the pole, F, right? The vertical component of that is F cos theta. So it is acting on the pole, F cos theta. And the horizontal component on the pole, the pendulum is F sine theta. It is like this, right? Now, in addition to that, you have the tangential acceleration of the pendulum because it's going in a circular motion with respect to the cart. With respect to the cart. So this is with respect to the cart actually, these motions. You can see if you take the pole length as L, it is now going through a circular motion with the radius L. So L theta double dot is the acceleration, tangential acceleration. L theta double dot. And then radially outward, you have another acceleration. That is a centrifugal acceleration, L theta dot square. So there are two accelerations, linear accelerations on the pendulum. One is tangential, the other one is radially outward. Okay. Now, I have indicated here two unit vectors. One is along the tangential direction, that is the direction of L theta dot, double dot rather. That is k theta. This k theta is a unit vector in that direction. So it's changing as the pole rotates. This k theta direction changes. It's a unit vector, okay? Because you are working with vectors, I want to assign this unit vector to refer to these accelerations, where acceleration is a vector. If you look at L theta double dot, is not a vector, it's a scalar. So when you multiply L theta double dot with k theta, it becomes a vector. And again, L theta dot square is the centrifugal acceleration. The direction is kr. This is radially outward unit vector in that direction. Okay. However, our principal coordinate frame has horizontal and vertical axis, like over here. So you have horizontal axis indicated by the unit vector I, and the vertical axis indicated by the unit vector j, ij. These are the familiar unit vectors in our coordinate frame. Okay. Now, based on the pole angle theta, right, you can see how k theta and kr, these two unit vectors, are associated with I and j. ing. So you can write down equations for kr and k theta in terms of I and j. Okay, because we can't have too many unknowns in our mathematical models. So if you refer to this diagram over here of the 4 unit vectors, we can resolve kr, for example, into I and j. So the horizontal component of kr is uh, this is unit length 1 5 times sine theta, and it is negative direction. You can see it over here, negative sine theta I. Then vertical component is cos theta j. Can you see that? Cos theta. This s theta is actually sine theta. C means cos. Okay. So that is the ij representation of kr. And then k theta, this direction, if you resolve this into horizontal direction, it is cos theta and negative. So it is negative cos theta I, right? Then vertical component is actually negative. It is sine theta, right? This angle is 90 minus theta. So it is cos 90 minus theta, that is sine theta. And j, it is negative because it is round. So now we don't need kr and k theta when we refer to uh, tangential acceleration or centrifugal acceleration. You can write down k theta and kr first and then immediately replace them with these equivalent ij expressions, right? Then we come over here to the pendulum equation. If you look at the pendulum, right, this is the pendulum, write the motion equation horizontally. The only force horizontally acting on the pendulum is f sine theta in positive direction. So we write f sine theta. So it should be equal to mass. Simple M is the mass of the pendulum times acceleration. So for the moment, we will write AX. A subscript X means the acceleration of the pendulum in horizontal direction. Okay. The pendulum actually moves up and down also. The vertical motion is also there. So you can write down the motion equation in the vertical direction. And there you can see the mass of the pendulum is there as a force. And in addition to that, you have F cos theta, again a vertically downward force. So you can write minus F cos theta minus mg. These are the two forces acting on the pendulum is equal to mass times acceleration in the vertical direction, ay. We don't know what ax is, ay is, but they are the horizontal and vertical accelerations of the pendulum. Okay, with respect to the earth, not with respect to the cart only. Okay, right. Now, I want you to pay attention to this particular diagram here. This is very important. Now, you can see some inverted pendulum models freely available online. And sometimes you will not see the friction, drag coming into the model. Most of the models are actually not considering the friction and drag, etc. So that's why this part is very important, because I have included in this modeling the friction. Of course, you can see this bx dot as the friction, right? And also you can see it over here on the pendulum as it moves with respect to the air. So there's some, because the velocity is in this direction, right? Major component. So q theta dot as the drag, air drag. So that is also included. It's not complete, I know, but at least this gives you a sense of completeness in your mathematical modeling. Okay. So this q theta dot is actually uh, the resistance, right, to the motion because of the air drag, basically. Okay. Now, uh, if you look at the total torque, right, on the pole, which causes the motion, right, um, part of that torque is to be spent to overcome the friction, the drag, etc. So we can write tau t, that is the total torque, minus tau d. Tau d is actually the resistance, whatever forces, torques rather, against the motion, right? You have to take that part out. You can't use 100%, right? So a small amount should be spent on all the imperfections in the system. And then the remaining amount is t tau, which causes the motion, Okay, so this tau, right, uh, produces heat double dot. Okay, and this tau d, the resistance force, produces q theta dot. It's like corresponding, right, to this particular uh, quantity, that is q theta dot. And therefore, the total torque over here, right, we can say it is actually corresponding to some theta double dot t, right, which we don't see actually. That theta double dot t is not what you see. What you see is only this one, theta double dot. However, you know that your entire, if you look at the energy perspective, right, it is tau t, the total torque, which goes in, right, and it is this tau torque that comes out as a outcome. Okay, so in your equations, we need to write down components, right, referring to total torque here. Otherwise, there would be energy imbalance in your equations, right? So keep that in mind. Right. So with that, I write the acceleration, right? A of the pendulum, simple A. This is acceleration of the pendulum. I have to consider all of the acceleration, right? Horizontal, vertical, etc. So I first write x double dot I, which is the acceleration of the cart. Pendulum is on the cart. So therefore, whatever acceleration um, that is there on the cart, right, um, is applicable to the pendulum as well. So pendulum gets x double dot I, horizontal direction, this linear acceleration. Okay, and in addition to that, it gets L theta double dot plus q theta dot coming over here, right? The total acceleration, uh, theta double dot plus q theta dot, these two components together, two accelerations, and k theta. K theta is the direction of that vector. Okay, so in this direction, plus L theta dot square kr, that is this direction, L theta dot square. Okay, so the second term is the tangential acceleration. The third term is the centrifugal acceleration with their respective directions uh, defined by k theta and kr, plus x double dot I, that is the acceleration of the cart. So these are the three acceleration components of the pendulum. Now what we do is we replace k theta using this expression over here and kr using this expression over here, and substitute them to the second line of this equation, so that the second line has only I and j, horizontal direction and vertical direction. After that, I assemble I terms to the uh, uh, immediately after the equal sign, and then all the j terms after that. Okay. Now you can see the items x double dot minus cos theta L theta dot double dot plus q theta dot minus L theta dot square sine theta. This is the I component, that is the horizontal acceleration of the pendulum. And then the second term minus sine theta times L theta double dot plus q theta dot plus L theta dot square cos theta, right? That is the total acceleration of the pendulum vertically upwards. So this is actually the AX in this equation, second equation. This is actually AY that was there in equation number 3. Okay, so why I uh, explain the entire thing today to you is to refresh your memory on modeling. And when you are dealing with a relatively complex plant, right, this is the type of approach. Okay, you have to write down, you have to draw the system and get the free body diagrams and then assign the vectors and look at the energy balance and then write down the basic equations of motion, right, like that. I hope this will help you revise your uh, basics, right, in modeling. All right. Now we have two equations, AX and AY, horizontal and vertical accelerations, right? Now you can substitute these two expressions to equation number 2 and 3, okay? So when you do that, right, expression 4 goes to equation number 2, and this is equation number 2, how it changes, and we have number 6. Okay, you simply substituting the vertical acceleration, sorry, horizontal acceleration from equation 4 to equation 2. You get this one, and from 5, that is this one, vertical acceleration, you substitute that to equation number 3 to get equation number 7. All right. After that, what we do is, if you look at these two equations, 6 and 7, right, you can get rid of F. F is the force along the pole, okay, the tension of the pole. We can eliminate that using equation 6 and 7. What we do here is that we multiply equation number 6 with cos theta and equation number 7 with sine theta and add them together so that F goes out and we get this equation. All right. Then you take x double dot, that is the highest derivative of linear motion, and theta double dot, that is the highest derivative of the angular motion, motion of the pendulum. Cart motion, pendulum motion. The highest derivatives are like second derivatives here. So we take x double dot term and theta double dot term to the left hand side and bring all the other terms to the right hand side, and we have equation number 9. Okay. So this is one of the major equations of the pole part system, where you have x double dot and theta double dot on the left hand. Now, this is not enough. We need another equation because we have two acceleration, x double dot and theta double dot. So we need to have another equation. Of course, we have one. We have not used yet. Equation number 1. So what we do is, again, you have f sine theta. We want to get rid of this one, f sine theta. So you can substitute from here. F sine theta is equal to max. Ax is over here. You take ax and put it over here with m and put it back on equation 1. Okay. So there won't be any f. anymore. So when you do that from 6 to 1, this is that equation. Look at this m f sine theta. This is f sine theta part. Okay, from here, equation number 6. This is f sine theta. Goes to equation number 1. Once you simplify the equation, you get this one, equation number 10, right? M plus simple m x double dot minus m cos theta L is double dot. Again, you can compare this with equation number 9 over here. You can see x double dot is double dot. Here also, x double dot is double dot. And you have very nice two equations, number 9 and number 10. So using these two equations as two simultaneous equations, you can actually find out expressions for x double dot and theta double dot separately. Okay, all these steps are here. Right, I will distribute this note to you. You can read all of the steps very carefully. Right, I don't want to spend a lot of time on going each and every term here. I have checked these equations, all of these things with myself. So check again and again. So if you find any errors, let me know. But I don't think that there's any error here. Okay. So now what we do with equation number 9 and 10 is that we multiply equation number 9 with m cos theta, negative m cos theta, and add to equation number 10. So when you do that, this uh, m cos theta term, which comes over here, theta double dot term cancels out when you do that. So eventually you isolate x double dot on the left hand side, and this is the equation for x double dot. Okay, this is x double dot equation as a function of all the other variables. Like you have theta dot, you have x dot, you have theta, right? It's a nonlinear equation. It's a highly nonlinear equation. Similarly, you can use the same two equations, 9 and 10, to get rid of x double dot term and isolate theta double dot. Okay. So when you do that, this is the equation you get. This is a bit long equation. Theta double dot is, it depends on u. U is the force on the part. Theta dot, pole velocity. Theta, pole angle. X dot, part velocity. It depends on so many things, and you see sines and cosines and squares. So it's a highly nonlinear plan. Okay. Now, if you look at this in the context of state space modeling, you can write these equations. Say, for example, x1 dot is equal to x2. This is state space modeling, and x2 dot is equal to x double dot. That is equation 11. This one. Okay, x double dot acceleration of the car, and then x3 dot is equal to x4, and x4 dot is equal to theta double dot. That is equation number 12. This one. So the first two equations describe the card position. The second two equations, equation 3 and 4, explain the pole motion, right? So x1 is the position. So x1, x2, x3, x4, like in any state space model, x1 is the linear motion of the card, x2 is the linear velocity of the card, and x3 is the angular position of the pole, theta, and x4 is the angular velocity of the pole, right? That is theta dot. Then when you write down the state space model, on the left is the rate of change of the state variable, right? x1 dot, x2 dot, x3 dot, x4 dot. Okay. So x1 dot is the velocity of the car, and x2 dot is the acceleration of the car. And for that, we have an equation. X3 dot is the position of the pole, sorry, the velocity of the pole, this dot, and x4 dot is the acceleration of uh, the pole, that is theta double dot. And for that, we have this equation 12. Okay, and the parameters of the plant are mass of the cart, mass of the pendulum, uh, the pole length, then drag coefficient, friction coefficient, gravity, etc. Okay, right. Now, when you have the system model like that, okay, first thing you need to do is to go to a simulation platform like MATLAB and write down these codes, because we have the two equations, right? Explaining the motion, x double dot, theta double dot. So you can start from any point, right? Any x double dot, any theta double dot, okay, as initial conditions, and then run these two equations and see what happens. Okay, so I can show this to you, this little code in MATLAB was written to simulate the cart and pole motion starting from a certain initial position. Okay, there's no controls whatsoever. This is free swinging. If you start from a certain initial position and let the system go, it will freely swing back and forth. Okay, so we want to see, first of all, and verify that we have got the mathematics correct. Okay, right. So this is the MATLAB code for that. So there you can see the system parameters like this, right? Uh, Pole length, gravity, drag coefficient like that. Uh, and then you can see over here the initial condition, right? You can see x is 0, x dot is also 0. Cart is actually standing still. It's not moving at 0. And you have theta 40 degrees, right? 40 degrees from the vertical, 40 degrees. And you keep it there and let it go. So there's no initial theta dot. There's no initial angular velocity. You just deflect the pole by 40 degrees and release from there. That's all. Okay. So then let's run this code and see what happens. Right. So this is the initial position, 40 degrees. Now it is swinging anti-clockwise. Can you see that? It falls below the horizontal line. And as it happens, you can see the top two graphs showing cart position x and cart velocity x dot on the top left. And on the right, you can see the theta, pole angle, and angular velocity of the pole, right? Now it has completed almost one cycle, and then it goes again, right? It's falling back. And we have introduced friction for the cart motion, left and right, and also air drag, that is the resistance for the rotary motion, also in the equation. Therefore, through the motion, energy is continuously dissipating. So therefore, you will see this motion is actually settling down gradually. Okay, it doesn't rise as much as it was in the previous cycle because it loses energy, right? So I want to mention that this is extremely important part in learning, especially control systems. You model the plant, you then code it in MATLAB, and then visualize it. Okay. Not only the graphs, now you can see some sort of animation happening so that it like builds your confidence. This is exactly what we have seen, right? Of a pendulum swinging back and forth, right? It should reflect our experience, right? Our simulation should be very similar to what we already know about a swinging pendulum. If it is a very different thing, of course, there's something wrong. Okay. Now, again, if you see the two peaks over here, you can see, right, this is X, the blue one, and the amber one is the velocity. You can see the peak velocity reduces, right? Look at the first two peaks. Peak velocity reduces. The peak velocity comes when it swings vertically downward. Okay. So when the pendulum is completely vertically downward. So like if it is swinging like that, this is the maximum velocity point. So the first one, it has some higher velocity, but the second one is a bit lower. And gradually it is dissipating its energy. That's why. Now, when you get to this sort of simulation, right, now you can say that, okay, you have come to a uh, uh, certain milestone in your process. Now you have at least a correct simulation. Okay, right. So let me stop the simulation. Right. And go back to the lecture note, right? So now we have the simulation. Now, can we design a controller? Can we design a controller? Well, uh, it is a bit difficult than you initially thought because the two equations we have right now are highly nonlinear. So therefore, what we do is that we ask, okay, can we linearize the plant? Okay, so how do we do that? You saw in your simulation that it was swinging almost 360 degrees, right? But if we assume that we start almost vertical, right, with a little deflection back and forth, but not too much, we can do certain assumptions, right? For example, for small angles, sine theta is equal to theta in radians, and cos theta is equal to 1, okay, like that. And theta dot square is 0 because it's close to 0, right? When theta dot is small, right? If you don't have initially any velocity, right, it's almost 0, theta dot, but if you assume a small velocity, square of that is even smaller. Then you can simplify x double dot equation into this one. And also theta double dot equation, which is a nonlinear equation, into this one. Can you see that? So you simplify the two equations and then you can find out theta x dot theta dot, right? And on the left hand side, x double dot theta double dot. So you can separate the state variables very easily as x dot theta theta dot. These are the state variables. These are the rates of the same state variables. Okay. And plus the control signal u. It appears in the second equation and the fourth equation. Okay. Now this is a linear model. You can use this model to design a linear quadratic regulator very easily. Okay, we have done all these things earlier. However, you need to remember that you have done a serious assumption that theta is nearly zero. So you should not use this controller you are going to build. Okay, so the first equation over here is the linearized uh, x double dot, assuming approximately vertical pole configuration. Okay, so it should be like this, almost vertical. Okay, not like this or that. And the same configuration, theta double dot equation, which is highly nonlinear, would eventually become like this. And then you can have the linear state space model. So this is what is called the linearization. Okay. So it has pros and cons, right? Pros is now you have a linear model, so that's easy to design the controller. The con is, negative side is, if it goes out of this area, right, where you linearize the equation for, right, you cannot expect good controls, right? So then what we learned so far is these things. The card-pole system is highly nonlinear. And in plant modeling, it is important to include dynamic disturbances such as friction and drag. So wherever possible, try to include uh, friction, drag, and that kind of basic disturbances. Okay. Otherwise, the model that you have would be highly idealistic model, which is not practically um, complying to any practical conditions. Okay, right. But initially, you may assume frictionless, dragless condition to get to build some confidence, but that's not enough. Immediately after that, you have to introduce these disturbances, right? Then the third one that we learn is nonlinear dynamic model can be linearized around an operating point, right? You can't do this anywhere. In general, for a given plant, there is a certain one or many operating points. So you have to linearize your model around that point. Okay. Then fourth bullet, the differential equations of the plant model and its linearized model for the state variables and how they are connected. That is state space model, the connectivity of the state variables. It also shows how the control signal is connected with the states. Okay. So as you saw in the state space model, right? Over here, you can see the control signal U and it goes into the second equation and the fourth equation. So that you can actually use your control signal to influence x double dot, that is the cart acceleration, and theta double dot, right, which is pole acceleration. Okay, now this is very important. So it is just a single control signal that you can use to control two variables in the system, theta double dot and x double dot. But remember, this statement is valid only when the pendulum is at vertical, nearly vertical position. Okay, if it goes like that, all of these statements that I'm making here are not valid. Okay, right. Then the last bullet, the linear model of the plant can be represented by the state space model, that is ABCD, to know it, leading to linear control design. Well, this is the linear controller design. Right, 2 weeks back we did the linear quadratic regulator. Right, if you have the plant, this is the plant, right? The linear model of the plant, A, B, C, D, four matrices. You can use MATLAB and use this state space block, right, on Simulink and open it and put A, B, C, D. And in your MATLAB code, you have A, B, C, D clearly described, okay? This matrix, this one, for given mass, length, drag coefficient, etc. You know this matrix very well, okay? And also this vector. So then this is just piece of cake. And then you again design your linear quadratic regulator for a known system ABCD, okay? And you put the desired position of the card, right? That is x1 for state variable. We want to move the card to a certain point, and all the other variables you need to stabilize to 0. Okay, so you can see all these three states, x2, x3, x4. This is the path velocity, it should be 0. And then pole angle should be 0. Pole velocity should be 0, right? Only the position should be adjusted based on this desired position. Okay, right. Now, this works with the full state feedback, right? The linear quadratic regulator here uses full state feedback. You can see it over here. The Simulink model produces 4 states, okay? All these 4 states go as input to the linear quadratic regulator, right? So this is how the linear quadratic regulator works, right? 4 states, x dot, theta, theta dot. They are multiplied with 4 gains. These are the 4 gains in the linear quadratic regulator, okay, with single control signal, that is u, okay. So when you multiply this, you get actual u, okay, single control signal. And these 4 gains are found in MATLAB using LQR command, right? For that, you need to refer to the notes 2 weeks back and MATLAB codes on the linear quadratic regulator. So here, just to mention you what it does is that it optimizes a certain function, objective function, let's say cost in this control, right? So you start the pendulum with a certain angle and the linear quadratic regulator will stabilize it and move the card to the desired position. For that duration, whatever it is, what is the total cost? It is given by this integral over here, x transpose qx plus u transpose ru, where x is the state variable vector. And if it is not 0, it is a cost. And the control signal, what sort of controls we are using? So we are spending energy for control signal, right? So this is the total cost, and we want to get the integration from 0 to final time and then minimize it, right? In that process, we calculate what is K1, K2, K3, and K. All right. And we have to specify Q and R. Q means how costly the errors are, right? In the 4 states. If they're not 0, how significant is that and how costly is that, in other words, right? And U, the R actually, okay, we specify R, our own, saying that, okay, my control signals are expensive or cheap, right? If I use petrol, for example, for this controller, and if petrol is very cheap, this R is very small value. It's not significant. But if I use petrol, which is very expensive, then R is a higher value, like that. Okay. So this is your matrix, system matrix, same matrix over here, right? This is how it looks like in MATLAB, and BCD, right? And we prepare the state space model of the card pool. And then this is my Q matrix. I have given 10, 1, 50, 100. What is that? 10 is the first state variable, x1. x1 is costly. That is why I have put 10 here, somewhat costly. This is x dot. It's not very costly. I put 1 here. I don't ask me why I know that. These are just intuition. Then x3 is the angle, 50. I don't want to see any big angles, right? So it's a bit costly. And this is angular speed. That is very expensive, 100. If I have high speeds, that is not good. So therefore, I put a bigger cost here. R is 1. And this looks like cheap control signal, right? You can spend a lot of energy and it doesn't cost much. And in MATLAB, this is how you generate your linear quadratic regulator gains, LQR gains. Once you know A, B, Q, and R, you know K. K is the linear quadratic regulator gains, this one. Okay. So in your MATLAB simulation, uh, it goes over here, the gains. Okay. So with that, everything is ready to go. So now you can simulate the plant, this plant, right, with the linear quadratic regulator. So let me run this for you to show you the system with feedback control, right? So this is a linear quadratic regulator in action. Try to stabilize the inverted pendulum and move the car to a desired point. Again, you can see over here the same system. I start with, let's see the animation first. Now see, I start with some angle, but now it doesn't fall like what you have seen earlier, right? Because the control signal pushes the card to the negative side, avoiding the pendulum falling over, right? Now, can you see that? We are moving the card, the LQR controller, right? It's moving the card to sideways, right? Now it goes to the left side, but I think we want to bring the card to 0.5, somewhere over here. That is the reference point, right? We want to finally bring the card to that point. Okay. So the way the LQR works is that it has to bring the card first to the negative direction to stabilize the pendulum, right? And then it moves to the right. So pendulum, card cannot move to the right straight away, even though the reference point is at 0.5 meters because of the card position. When the card position is like that, if you move this way, it will fall down, right? Therefore, based on the card position, it has to move in the opposite direction first and then come gradually, right, to the reference point, that is 0.5 meters. Now, this is how you design and build a controller, right, for a plant. In Simulink, you can do all these things uh, and verify that you have a good controller. Okay, so eventually it goes somewhere over here, 0.5, and settle it there. Right. So I don't want to continue this one. Okay, but look at the graphs here, right? The card position and card speed, right? Goes like that. Card position is to be stabilized at 0.5 meters. So it should be somewhere over here. Now you can see it is coming there, right? Coming there. The blue one coming to 0.5 meters. And over here you can see the angle. It is already stabilized, right? Now the pole angle and the speed are both nearly zero, right? And then it's only the position that we want to control. Okay, fine. Now, what is next? We can do something really interesting here. Uh, can we use the same linear quadratic regulator, right, that we design and build based on the linear model, right? Yeah, using the same linear quadratic regulator. What if we replace the linear model with the actual model? The actual model in Simulink, you can do that using Simulink function. This one, okay. So the Simulink function runs the nonlinear equations x double dot and theta double dot. You can see the two things over here, x double dot, theta double dot, but it needs control signal u, theta and theta dot, okay. And I think x dot is also required, this one. I have to modify this one. I think x dot is also required. X dot is over here. This is x double dot, this is x dot. There should be a link over here, from here to here. I'll check that out. So now here, you are running the nonlinear model of the cardboard with a linear controller, right? It is not the right way, but it's a very significant step in your design process to see how far the linear quadratic regulator can cope up with the nonlinear dynamics. Okay, because earlier your simulation was based on the linearized model, and we know that it is not very accurate. Okay, but now we know the nonlinear model is the accurate model, so we can check whether the linear quadratic regulator is able to stabilize the plant. Right, there you are. Can you see that? So there should be x dot u, theta, and theta. Because in our equations, we show these variables, right? If you go back to the PowerPoint, right? Uh, I can show you the two equations over here, right? Theta double dot, it depends on theta dot, theta, and x dot. So you need these variables to run your nonlinear model in Simulink. Okay, here. So I will update this slide. Uh, now, this is the nonlinear model. So if I open this up, right, uh, you will see the functions, right? It's not opening because simulation is running. That's why. Now you can see the simulation over here. Not too bad actually, right? The same linear quadratic regulator is still able to stabilize a plant, right? When you have the true dynamics, nonlinear dynamics. But if you look at the graphs over here, they are swinging a bit too far now than it did with the linear model. Okay, so let me stop the simulation for a moment. Right, now I can open the Simulink over here, this block. It is a function, Simulink function. Okay, so it takes xt, that is x dot, control signal, theta and theta dot, and it calculates x double dot and theta double dot, right, using these two equations. These are the true dynamics, right? True dynamics of the plant. So Now we are much more confident that this controller is actually able to stabilize a plant, right? Because it's now working with the actual nonlinear dynamics. Okay, but if you watch this simulation, you would have seen. Okay, I think you missed it. With the linear plant, the cart actually moved somewhere over here, right? And then it came back, right? But when you use the actual nonlinear model, the cart moves beyond the screen. Actually, it goes out of the screen and then comes back. Okay, so that that tells us the difference between dealing with the actual dynamics and the linearized dynamics. Okay, so in case of actual dynamics, the linear quadratic regulator is not that good, so therefore it's not able to fully stabilize the plant, right? It goes too far back and forth. So what are the things that we learn here? First bullet, LQR needs all states available for computing the control signal, right? That is the force on the card, which is called the full state feedback. We have four states, right? Card position, speed, pole position, that is theta and theta dot. You need all four states. Then number two, LQR performance changes as cost weights for state variables, that is Q matrix, and control signal, that is R matrix, are adjusted. So, of course, you can adjust Q and R um, based on a certain situation. Okay, if you can handle large errors without any issue, major issue, then you can have Q small, right? And if you have your energy at a cheaper price, you can make R small, like that. Then the last bullet, performance of LQR degrades when the nonlinear dynamics is introduced and initial deflection is large. So if you have initial deflection large, right, like 15, 20 is all right, but when it goes to 30, 35, then you will see the performance degrades. So now what you do in that situation, if you still want to use Kalman, the linear quadratic regulator, but if you don't have the four states available for the measurement, right, you're going to introduce a Kalman filter, right? So KF is used to estimate some of the states so that only few sensors are required to implement full state feedback. Let's say you can have card position measured, pole angle measured, only two. But with that, you cannot implement full state feedback because you need all four. Then you use a Kalman filter, which takes the measured two states and estimate all four states. And you can use these four states coming out of the Kalman filter, fed back to the linear quadratic regulator, and you can run the entire system. So Kalman filter is an unbiased minimum covariance state estimator, right? It doesn't have any prediction error, bias, no bias, and it removes sensor noise and estimates the true states. Because when you have the two sensors to measure the card position and pole angle, anyway, you have sensor noise. You need to do some sort of filtering. So why don't we use Kalman filter, which will not only filter out the sensor noise, but at the same time estimate the other two states. Okay. And the Kalman filter is based on zero mean Gaussian noise. So when you buy the sensors, make sure the sensor noise distribution is zero mean and uh, uh, Gaussian. Okay, in that case, there's no problem with the using them with the Kalman. But as you know, you cannot use a Kalman filter or any other estimator if the system is not observable. So therefore, you need to first check whether the system is observable. I think you know how to do that using observability metrics. And do that. And if the plant is observable, you can go ahead and implement a Kalman filter to estimate the force states. This is the actual process now. The plant with the control signal and then the noise coming from the force states, right? The process noise. This is much more realistic. Earlier simulations are not that realistic because it didn't have any sensors, any noise or anything. Okay. Now you are developing your system more towards the practical situation where you have to deal with sensors and noise therein. So this is this is not the sensors, this is process noise. Any unmodeled dynamics, right, appears when you try out your controller with the actual system, right? And this is where the sensor noise comes in, right, in the measurements. Okay. And you know how to deal with Kalman filter also. We have completed that some time back. So how do you modify your system with the Kalman filter? Now you can see the nonlinear model. We are not going back now. We are only going forward. So we are dealing with the actual dynamics. That is nonlinear model. Okay. And so these are the two sensors that we produce to measure um, the two states. That is card position and pole angle. Okay. And the sensors have noise. And we connect the two sensor signals to the Kalman filter, right? And the Kalman filter here is the standard Kalman filter, which is based on the linear model of the plant. Right? This is very interesting now. You have the actual nonlinear model of plant. You have the linearized model of the plant inside the Kalman filter. And the Kalman filter uses the linearized model and the signals coming from the sensors and predicts the force states. And these estimates from the Kalman filter goes as input to the linear quadratic regulator because the regulator needs all four states, okay, either directly from the plant or through the estimator. This time it is through the estimator. Then the quadratic regulator produces the control signal, it goes to the plant. Okay, right. So this is the result. By the way, here I have taken only one signal actually, not two both signals, just one signal. Right, that is the card position. I am measuring only the card position. I don't measure the pole angle. I don't know theta dot either. Right, I'm trying to see whether Kalman filter is able to predict all four states with just one measurement. Okay, so just out of curiosity, I'm trying this. Let's say, right? So this is the result I get. Kalman filter can actually estimate the position, path position, very accurately. You can see the two curves, right? Kalman filter estimate here in red and actual position in blue. So they are going together. However, over here, the pole angle and pole angle estimate are, are not equal, right? Initially, you can see somewhere over here, Kalman filter start with 0, right? but you start the pole angle with some value. Kalman filter doesn't know that value, start with 0, but it tries to gradually converge to the actual theta. But here it doesn't happen because we are not actually measuring the theta. We are trying to predict theta without any sensor signal. Okay, so therefore it's not going to work. It is a failure, right? So there's no point of showing you a simulator also. Therefore, we introduce two sensors. Now we have card position sensor and pole angle sensor, two sensors, right? When you have two sensors, your measurement equation is like this. You have two sensors, right? V1 and V2, right? And this is Y, it is a 2 by 1 vector, right? Two measurements. Uh, with that, this is your Simulink model, right? You have the nonlinear plant here, the two signals measured, card position and pole angle, and they are both taken into the Kalman filter, and Kalman filter predicts the four states into the linear quadratic regulator. It produces the composite, right? And this is what we get. So I can show you this simulation. Right. So various noise values, you get different signals, result rather, and this is for a particular one. You can see the pole angle, right? There's initial deflection over here, right? Uh, and the Kalman filter estimate is the amber color one because it starts with 0, but immediately it follows the actual data, right? And after that, it goes together with actual uh, pole angle with noise. Now see, because of this noise, you don't see very clear, beautiful graphs that you saw earlier. This is the reality, okay? Because the noise, you never get it perfectly like that, but it swings back and forth a little bit, right? And this is the card position, right? We want to set it to some value, right? It goes like that and then comes back and settle there, okay? So this is really good performance. Uh, I would say, look, and you can see it over here. Initial angle is big now, right? Still, we managed to do a really good job. So if I take you to the MATLAB code and to figure out what is the initial state, uh, it is still 40 degrees. You can see it over here. It's about 40 degrees. Okay. You start with 40 degrees and try to think. So we can change this to, let's say, 50 degrees or maybe 70 degrees. What will happen? Now it is 70 degrees. It's not good. Can you see that? This is 70 degrees and theta estimate are not complying each other. Uh, Part position is okay. This is the control signal. So this is not good result. So you can't handle 70-degree deflection. But if you what about 60 or so, right? What about 60 degrees? It's still not good, you know. Even we cannot handle 60-degree deflection uh, this way because you have a linear controller and Kalman filter is standard, which is based on the linear model, right? But the actual plant is unlinear. So what about 50 degrees? Um, well, that is also not good. We can reduce it further to 45 or to 45 degrees. There you are. Right now you have good control. All right. For 45 degrees, you can see the Kalman filter predicts the actual pole angle uh, reasonably well. And same thing is happening with the card position, and therefore we can stabilize the plant. Okay. So if you try a linear controller with a nonlinear system, there are limits. That is what we learn up to now. Okay. So it is good that we can at least go for 45 degree, right? 45-degree swing. But if the initial angle is more than that, uh, this controller is of no use. Okay. All right. Now here you see a linear quadratic regulator with a Kalman filter to estimate the four states using two sensor signals with noise, of course, right? So this combination where you have a linear controller, linear quadratic regulator working with the Kalman filter is called linear quadratic Gaussian. Okay. Uh, and there you can see the initial error in the Kalman filter in theta prediction. Actual theta is about 45 degrees, but the Kalman filter starts with 0, but it quickly converges to the actual value. And after that, even though there's huge noise in theta measurement, a Kalman filter is able to predict uh, pretty accurately the actual theta, okay, removing the noise. So that the linear quadratic regulator doesn't have to respond to noise here. It will only respond to the Kalman filter estimate, which is the red line over here. Okay, right. So this system will bring you to about 46 degrees and you can stabilize the plant up to that point. So 45-degree deflection initially, but the LQR with Kalman filter is able to stabilize the plant. Okay. So 46 degrees is quite big value. But if you look at what we really want to do overall is to stabilize the plant with even very big disturbances. So therefore, this is not enough, right? So these are the points up to now, the learning points. A state estimation is an efficient way of producing state variables for full state feedback, right? Such as pole placement or LQR, full state feedback. The plant needs to be observable for state estimation to work. So you cannot produce states from a Kalman filter or a observer if the plant is initially not observable. So therefore, it should be observable in the first place. Okay? You need to check whether the plant is observable. By the way, the Kalman filter here is a linear Kalman filter. So therefore, you use A, B, C, and D and observability matrix to do that. Okay, so all linear. The Kalman filter and the controller, they're both linear. Your system is nonlinear. Okay, so the Kalman filter removes noise in state variables. However, noise must be small enough to maintain accuracy. So if you have a big noise, then again your performance degrades. Okay, and the estimation of loosely coupled state variables R this is when you try to use just one sensor to estimate the other three states. It is not very accurate. And we saw that this way, Kalman filter is not able to actually predict the pole angle. Okay. Even though theoretically you can complete the loop, right? Close the loop rather, but you don't have the accuracy. So therefore, you need to have sufficient number of sensor readings, right? Even for the Kalman filter to estimate states accurately. So then, when the pole angle is also measured with the card position, state estimation became more accurate and persistent. Okay, so the two sensor case versus one sensor case, and we have seen that there's no need to measure other two states x dot and p dot because Kalman filter can accurately predict these two, and you can go ahead with the linear quadratic regulator. Okay. Now, the next step is to replace the Kalman filter with what is known as extended Kalman filter. So we are getting one step further, right, into making the system more versatile, more capable, right? So you can see much of the Simulink model remains the same, right, as you saw in earlier case, except the right lower part over here. There you can see the standard Kalman filter that was there earlier, but on top of that you have the extended Kalman filter, right? So extended Kalman filter is a nonlinear filter, whereas the standard Kalman filter is a linear filter. You can see the A, B, C, D. These are coming from the linear model of the plant. Okay, now you have the nonlinear plant here and nonlinear Kalman filter. So this should be bit more advanced, more accurate than what we had earlier. Okay, but still the controller is linear. All right. Now I want to show you how you bring in a extended Kalman filter. There are a few things you need to know. Number one, in the Simulink, this is how it looks like. You can drag and drop extended Kalman filter from the Simulink block library. Just drop it over here, right? And then you connect your control signal, which is this one, and your measurements, right? We have two measurements here. One is the card position, this one. The other one is the pole angle, this one. Okay. And inside the extended Kalman filter, right, you have to write down the nonlinear dynamic equation, just like what you had earlier here. All right. So I'll show you how this happens, right? Uh, so this is the model for that, and you have the let me run it. So this is the Simulink block, part wall LQG Y2 Zing. Okay, so let's give it a run. Then you will see the Simulink block open. So takes a little while. Right. So let me first take you to the simulating block. Right. So all of the blocks are already known to you, except the extended Kalman filter, this one. So let me open it. So when I open the extended Kalman filter block, right, you can see where you need to do certain settings. For example, you need to have the function over here, like state function, state transition function, right? So it's a MATLAB code in the same directory, state function. So if I go back to MATLAB, right, you can see over here, state function, this one. Then measurement function 2, measurement function 1, right? So you have to tell in these two small MATLAB codes, what is your first measurement? Because you have two sensors. What is your first measurement? What is your second measurement? Then you have to also tell how the state changes, like rate of change of state variables. Okay, you have four state variables. You have to write down the equations for the rate of change of the four state variables. In other words, the Jacobian matrix. You have to write down your Jacobian matrix. Jacobian means, first derivative, okay, partial derivatives uh, of the entire uh, state vector. Here we have four states. So rate of change of all four states. So if I open the state transition function here, you can see it over here. State transition function, right? It takes x and u as inputs because rate of change depends on the present state and the control signal. Okay, so you can see it over here. X is equal to, look at this part over here. X is equal to x, that is the state that was there, plus xd. And then the xd means the rate of change of x, right? X is the position over here. And this is the velocity, right? This is theta d, that is the rate of change of theta, theta dot. This is theta double dot. Okay. So these two equations we already know from the dynamic model. How this is theta double dot, x double dot and theta double dot. Okay, rate of change. So you bring these two equations from the model and write it as a function here, right? And then you go to the Simulink, right? And open the Simulink block and write down the MATLAB code name over here. So when the Simulink runs, it looks at this particular MATLAB code and it takes the present state and the control signal, right? Control signal is coming over here, right? And it can compute the rate of change and it knows the sampling interval and it updates the states. That's what happens over here. And if you look at the two other inputs, the two measurements, right? So they are coming as two other MATLAB codes, measurement 1 and measurement 2. So if you go to MATLAB, you can see the two measurement functions, right? Let me first take measurement 1, measurement function 1. I'm opening it up. It is very small, just 3 lines. First one is the function, that is y output, and then n. In between just one line, y is equal to x1. X1 means the first state variable, that is the position of the car. You are telling that you are measuring the first state variable, only that. Okay. And then what about the other one? Measurement function 2, you say y is equal to x3. That is the third state variable. that is angle. Okay, just that. So then in the Simulink Kalman filter block, it knows that this is how the states change from person to the next, and these are the rates of change of all four states, and these are the measurements, two measurements. Okay, so then it produces the output, it goes to the linear quadratic regulator. So once you do that, this is the result. Can you see that? Uh, Now the angle is, what is this angle? Uh, Let me go to this one. This is the function. The initial angle is 60 degrees. Can you see it over here? Earlier, we were not able to go beyond 45 degrees or so. Now we are simulating this with even 60-degree deflection, right? But we get better performance now. Can you see that? The extended Kalman filter is able to estimate the position. This is with some noise. You can see the noise here, right? But the y-axis is bigger. That is why you don't see the noise so large, right? But it is noisy. Accurate prediction, right, or estimation rather, for pole angle and card position is there. Earlier, the linear Kalman filter or standard Kalman filter had some errors before that, right? So beyond 45 degrees, it was not possible. So now we have pretty good results, right? So this is the control signal, and so I think we are happy about this result. I have explained these things to you. Just have a look at it. Extended Kalman filter needs to know the rate of change of each and every state variable, and you write this down as a MATLAB function. Look at this one, function x is equal to state transition function xu. You indicate in the Simulink extended Kalman filter block state transition function, this name in the top page, right? And you write the MATLAB file and keep the file side by side with the main code. Okay, same folder. You have several M codes. So this is the rate of change, Jacobian matrix of the plant. Okay, and the measurement function, right? And this is the result. So you can go up to 60 degrees. You can stabilize a plant from an angle which is even as big as 60 degrees. But if you go 65, right, then you will see even the extended Kalman filter cannot cope up with this thing because you don't have proper controller, right? Now it's eventually comes to the controller. The controller is linear, still linear, and of course, you know, there's only so much to be achieved with a linear controller on a nonlinear plant, right? So therefore now all focus is on the controller. How can we change the controller to go beyond this point, beyond 65 degrees? For that, we need to use nonlinear control. Okay, so I'm going to show you one of the nonlinear controls, which is known as feedback linearization, right? It is somewhat easy to explain. Uh, for that, I take uh, the dynamic model of the pole card system, right? Remember equation number 11, that is card acceleration, x double dot, and pole acceleration, theta double dot, right? So these are the two equations uh, from which we started this discussion, right? First couple of slides, we derived these two equations. Now we are not going to do any linearization anything because we have done it, and uh, I think we did a good job. And we eventually were able to control the plant um, up to about 65-degree initial deflection. So that is a good achievement. Now we are looking at the other side. So first of all, we will write these two equations, x double dot t double dot, as a matrix equation, and then take this u and this u cos theta. These terms are the external input to the plant, right? The control signal. So we will write these two terms as a separate term here, right? This is the autonomous system. System changes its on, and then this is the external part, right? Exogenous control. Then what we have is something like this, right? Uh, x double dot, theta double dot. We have two, let's say, two-state system, right? And then the autonomous part is F1, F2, right? F1 is this one, this is F2, plus G1, G2U. So this is G1, this is G2, okay? Something like that. So this is the nonlinear plant we have. So this looks similar to state space model, but it is significantly different because F1, F2, G1, G2 are nonlinear functions, okay, of various combinations of state variables. Now, let's say we want to stabilize the plant. Let's not worry about the positioning of the cart, right? Stabilizing the pole vertically. So that is the second equation over here. X double dot equals F2 plus G2 times U, right? So we'll write down that equation, right? So for the moment, I disregard cart position, right? Now, if you look at this equation, this is the uh, pole dynamics or pendulum dynamics. And if I select U, the control signal, in this way, this is not a uh, statement that was like uh, that comes with a proof, but with some intuition. Because we are experienced in this field, right? We have been through many courses and we know how it works. So therefore, you can generate some ideas. What if we try out a control signal like this? Okay. What is that? 1 over G2. G2 is this part. Times minus F2. F2 is this term. Whatever it is, nonlinear terms. Plus K1 E theta. Plus K2 E dot theta. Plus theta double dot R. Does it make sense? Now, what are these terms over here? New terms, right? K1 and K2 are gains, control gains, right? So that's not a problem. What is E theta? E theta is theta R minus theta. That is reference angle minus actual angle, right? So what is the reference angle for inverted pendulum? Of course, it's zero. Okay. Uh, what is theta? Theta is the actual angle, right? So this is the angle error. Then E theta, E dot theta is the rate of change, of the angle error, that is theta dot r minus theta dot. Okay. What is theta dot r? Again, you can say you don't want any reference speed. You want the reference speed, angular speed, be zero. So this is also actually zero, right? So this is theta dot, whatever it is, actual value. Theta r is the reference angle, right? What is the reference angle? Of course, it's theta, it's zero. Now, if you from the control signal, you know that the control signal is related to reducing the error, reducing the rate of change of error, and it depends on theta double dot r, right? So required theta double dot, right? So therefore, it makes sense. This is how the control signals are actually generated in principle. Now, when you bring this to the equation over here, you can write this equation again as over here. Theta double dot is equal to F2 plus G2 times U. U is this term over here. And you put it over here. Then what you see is that G2, G2 cancel out. Then F2, F2 cancel out. What remains is theta double dot R, right? This is theta double dot R, and this theta double dot goes to the right hand side as negative, plus K1 E, K2 E dot theta plus K1 E theta is equal to 0. And immediately after that, you will see that theta double dot R minus theta double dot is actually error acceleration, second derivative of the angle error. So that you can write down this equation as E double dot theta, that is acceleration error, velocity error, position error, with some two gains K1 and K2 is equal to 0. And this is very interesting because when you see the error dynamics, remember the error dynamics we discussed some time back. When you have the plant with this kind of error dynamics, you know that the plant is asymptotically stable, which means you can stabilize a plant. Okay. So if you start with some error initially, right, it will go down to 0 like that. Okay. Well, what you need to do is to adjust K1 and K2 appropriately. So for that, what you do is you take the Laplace transform of this equation, then it becomes a square es theta, and this is s es theta. This is e s theta. Okay. Then from that equation, you can pick up the characteristic equation without e terms, es, es, es. So what you remain with is s square plus k2s plus k1 is equal to 0. This is the characteristic equation of the plant, right? And it is asymptotically stable. Now, if you want to have, this is a second order system now, right? Two poles. So if you want to have the two poles like on top of each other, critically damped system, like this, right? On the S plane, you have the two poles, both of these poles on top of each other. So minus alpha minus alpha. You can write down the characteristic equation as S plus alpha times S plus alpha, which is S square plus 2 alpha S plus alpha square, which is equal to the characteristic equation that we have here, that is S square plus K2S plus K1. Then you can calculate, you can figure out, okay, K2 is equal to 2 alpha and K1 is equal to alpha square. Done. So assuming your alpha is 10, for example, minus 10, right? So then you can see this alpha is actually the actual value. This is negative alpha, but alpha value is say 10. This is 20. This is 100. So you have two gains, K1 and K2. K1 is 100, K2 is 20. Okay, so you place the poles over here and system is asymptotically stable. Now you go back to the controller, which is this one, right? You know K1, you know K2. At any given moment, if you measure joint angle theta and theta dot, okay, and you can work this out. You can calculate this entire term because F2 and G2 are coming from these two nonlinear terms, right? You can do the calculation inside the controller. Okay, this nonlinear terms are calculated inside the controller and generate U. And you put it up over here and you control P double dot. Okay, when you do that, this is your feedback linearized controller, right? There's no linear quadratic regulator anymore. Okay, you can still have Kalman filter extended version if you want with some noise and all that, right? But here I have just taken the actual two signals here. This is x dot, this is theta dot, this is theta, right? They all go to the controller. This is feedback linearized controller. We have two gains K1 and K2, and it calculates U, which goes into the actual plant, and you get the new accelerations, x double dot, t double dot. Okay, so probably this is your first nonlinear controller that you have studied. In the assignment, you will probably do this yourself, and let us see this in MATLAB simulator, right? So this is the plant, same plant, no difference at all. We don't have the linear quadratic regulator anymore, but we have the nonlinear plant. Okay, so let's go to MATLAB and see what we have there. Right. So I'm going to give it a run first. Then it will open Simulink. There you are. So I have some animation over here. Maybe I can run it again for you to see. Second, maybe I can show it side by side. This is very interesting stuff. Okay, so I'm going to run it again. See where the pole starts right now. It's a very big deflection. Okay, so if I come back to the MATLAB code to show you the initial deflection, how much is that? 120 degrees. Can you see that? Now we start the pole from 120 degrees. So which means from the vertical, right? 90, 120. Earlier, we couldn't even go beyond 65 degrees. Now we are going to 120 degrees here, right? So that's what the nonlinear control is capable of doing. Okay. So it doesn't matter where we are. We we deal with the actual dynamics, so therefore we generate the proper control signal for wherever the pendulum is. Okay, but I have to tell you this. If you look at the control signal, this is the biggest control signal we have seen. Right? It starts with some 300 units initially, positive, and then in very small time, it goes to negative 200 almost. Okay, because initially the pole was like this, okay, 120 degrees, and you want to get it upright. So therefore, what it does is it moves the card to the right quickly, very quickly, like a very jerky motion. Then this comes to the top with very high speed. Now you want to reduce the speed and stabilize. Okay, so that's how it does. It doesn't let the speed to take over. It immediately stabilizes in the negative direction and then stabilize the plant. Okay, this is a fantastic performance. But the problem is, do we have a good actuator to produce this aggressive controls? That is the problem, right? But without that kind of aggressive controls, you cannot actually recover the pendulum from a situation like that. Okay. Uh, but having said that, I also want to admit the fact that you can swing it back and forth, gradually building up the energy so that you can swing it up at some point and then stabilize. So for that, you need to combine different types of controllers together, depending on the state. Maybe you can use a linear controller, maybe a non-linear controller, or maybe some switch type of controls, right? Depending on where you are. The other thing I want to tell you is that this nonlinear controller only looks at the pole. It doesn't look at the position of the card. Card position is out of control. You cannot bring it back. Whereas in the linearized model, we were able to control both. Here, either of the two. Okay. So these are the pros and cons of nonlinear control. Again, what we have to understand is that there's no such thing like one size fits all. So if you want to handle a complicated problem with a very dynamic range, wide dynamic range, you don't have a single controller that is able to handle all these things, right? You need to switch from one controller to another one, right, depending on your operating point. That is the final learning over here. Right. Okay. So strong jerk is the problem here, as I mentioned. But otherwise, we have solved the problem. Okay. Right. So that's the end of the lecture today. Any questions, please?